Our next talk is titled Real-Time Monitoring of Helicopter Turbine Blade Temperature Using Passive Wireless Sensor. And this paper was written by Shrikala Susila, Taufik Orekan, Swadipta Roy, and Joshua McConkie, and Riamon Soto from Sensitech Propulsion Technology. And we have here Joshua McConkie as a presenter. Joshua McConkie has over 2 decades of experience as an instrumentation research engineer. A graduate of the electrical engineering program at UCL, Josh was the lead instrumentation engineer for the Space Shuttle Orbiter Discovery. Josh worked as the group lead of gas turbine instrumentation research at Siemens Energy for nearly a decade, where he generated 10 patents. Now he works to bring harsh environment wireless sensing to the market in gas turbines, advanced electric motors, generators, and other equipment as the CTO of Sensitech. Let's give Joshua a warm welcome.
Thank you. It's going to be hard act to follow. You guys are some crazy stuff. I love that we have MGT open to more technologies and systems now rather than just components and theory. And I'm going to be talking with you about that today. So what we're going to be talking about is a system that Sensitech has developed and now deployed that measures real-time wireless blade temperatures on turbines in very harsh operating conditions, up to 800, 900 C, full speed, full load, full throttle. The problem that people have when they're running gas turbines is that sometimes they run over the limit. And so the blades will break over time or suddenly due to vibration or due to melting. The temperature of the metals is not very well known because it's a very complex flow situation. They have internal cooling, they have radiative situations because the blades are experiencing 1,000, 1,500, 800 degrees C. And the materials just can't handle that without the types of protection systems that are actively deployed in the turbines. But sometimes those fail, and they fail in ways that are not known, but they're always temperature related almost. And so what we are doing is using all of standing on the giants of shoulders that have been presenting at this conference for 50 years. And we've built a wireless passive sensor system where the sensors are bonded onto the blades, and then we passively excite them and then read them at a nanosecond time frame in order to get their frequency. And that frequency is collected by our signal conditioner by Copper Mountain and then sent to our custom software. And then that frequency change is correlated, as I'll show you, to temperature. And thus we get the blade temperature, not the air temperature, the blade metal temperature of the turbine. And so the way that it kind of works is that the dielectric constant of the material is of the custom ceramics that we've made that are very stable and repeatable over time. That dielectric constant changes with temperature monotonically. And so that graph on your left is how the dielectric constant changes with temperature, and then the resultant resonant frequency resonators that we make change their frequency with temperature. So the temperature is the same on both. So as the temperature goes up, the dielectric constant goes up, and the resonant frequency goes down, and very repeatably. And so the way that it works is that we have our antenna, which excites the sensors. The sensors resonate within their body, and then that resonance is basically captured by the Faraday cage that we build around the sensor, which is the metallization that we put on the ceramic. That's not fully shown in here. That resonance will then change via the equation that's associated with the dielectric constant. And so that frequency change is what we're measuring. This is what our sensors look like. Here's one that is tack welded, which is a thin, very thin 4 mil sheet of Inconel tack welded around the sensor, holding it in place on the blade. This is what those bare sensors look like in shape and size. They're about the size of your pinky fingernail and about as thin as a tube. So their thickness is a 0.5 millimeter, 0.6 millimeter, 500-600 microns. These sensors work at extremely high temperatures. We've made sensors that resonate, not of this exact form factor, but that work up to 1750 C, which is 3100 F, and work as wireless sensors that we can detect at those temperatures. And then as well, the antenna that we utilize in order to read them can also go up to above 900 C. We'll show data where we took it up to 1070 C to make a measurement as well. And so we have to do that in order to go into gas turbines and jet engines, which is what our goal of the company was as it was founded. The antenna is made by terminating a silicon dioxide cable in order to create, we do some other stuff to it. We seal the silicon dioxide cable at the end so that there's no humidity going into it that changes its dielectric constant. We coat the center conductor with things like platinum and other things in order to protect that small little active section. And then we're able to turn that basically into an antenna. And the reason that we do that shape is that it has to be in the hot gas path. So because it's in the hot gas bath, it's experiencing not just high temperatures of 800–900 degrees C, but also basically sonic level flow, so Mach 0.8, Mach 1.1, and it has to sit there. So that we have to make it one-dimensional. If we made it two-dimensional, it would just be a sail and get blown out immediately. That antenna is also bendable, and so in this situation, we have the sensor is on the blade. We bring in the antenna out through the back of the exhaust. And then we have the antenna is about 1 or 2 inches farther from the sensor as the sensor is passing by the antenna each time. Now this is rotating by very fast. It's operating about 16,000 RPM, which is the equivalent of yanking on that sensor with 45,000 G. We have about 80 microseconds to read the sensor as it passes each time. Thankfully, we can do that because the sensor resonates on a time frame of about 45 nanoseconds. And so we excite it and then immediately get its ring as it's in the process of passing by. So the sweeps that we do are more like strobes as we get it. And we don't get it every time, but we get it enough times so that we can have multiple measurements per second to tell you what the blade metal temperature is doing, because the sensor is made of ceramic and metal that is very heat conductive, and so it is bonded to the metal. And so it takes the temperature from the metal, not the air, because it's placed right up against the metal. This is what it looks like installed. You can see we use tack welding, because basically we can bend our antenna, but it's very stiff because of the steel that it's made of on its outside jacket. And it holds in place even though what's coming out of the screen towards you is very hot, very fast. In this case, about Mach 0.7. All right, so this is just a better look at when we were installing the sensors. Because the sensors are thin and because we don't want to cause an aero trip, we don't want to trip what's called the boundary layer of the blades, so that laminar flow is not disturbed at the blades. We also create ways to make it so that the flow is wrapping around the sensor. And we've done a lot of simulations to show that there's no boundary layer trip, because we don't want to change what we're trying to measure by changing the heat transfer rate, by changing the turbulence of the local parts of the blade. We tried multiple different types of bonding methods. There's a silver braze that we found works up to about 23,000 G and works up to about 650 C. We tried flame spraying, which works in very different ways. We weren't able to fully grit blast the blades, so those didn't last as long. In this test, the silver lasted for about 25 minutes, this lasted for about 14 minutes, and this lasted for the full set of multiple tests, totaling more than an hour or so. And this is the tack welding, and that's the flame spraying, where I flame sprayed metal, which is a common thing, over the sensor. So there's many ways to attach them. We use epoxy for lower temperature things with our sensors. And the test that we did is in a T-53 engine, which is a turbine that's used on the inside. It's the powerhouse of military helicopters and other types of things. So this isn't on the blades of the helicopter, it's on the turbine that's actually running inside the helicopter. So it's basically a jet engine inside the helicopter. Here's what our system looks like when you're actually making a reading. So this over here is the time domain. And so we hit the sensor with the RF and the sensor rings. The sensor rings, and so we look at that ringing section, we extract the frequency from that, and when we do that, we get a very sharp, nice, high, regularly over 100 Q peak with a good 10, 20, 30 signal noise level, dB signal noise level. And this is what the antenna looks like when it's not reading anything, and this is what it looks like when it's reading the sensor. And so we get a very strong frequency reading of the sensor that our software can delineate in real time. And then in real time, we convert that using our calibration curves that we've already created in the lab. We convert in real time from that center frequency and how it shifts to temperature via our calibration curves. We do a 7-point calibration curve that we do with 1/100th of a degree C accurate SBRTs. I like the blowtorch pictures too, I keep putting those in there. This is a test we did with this sensor where we took it up to 1070 C in our ovens. This is in our oven test. And then let it just cool back down adiabatically. This is about a 3-hour test. But you can see that we consistently and well showed up to 1070 C, which is about almost 1700 F. And this is what our software looks like. We can just real-time graphs the temperature during the test, but it also records it so you can analyze it later, recording the frequencies and the temperatures. So this is the T53 turbine. Again, you've already seen kind of this picture. This is what it looks like on the outside. And so we have our antenna just poking in the back, tack strapped down, and then at Embry-Riddle University, which has been wonderful to us, they let us run it in their test cell with their engines and let us put our crazy stuff on there, which we've done with a number of customers now, so it's not so crazy because we've been doing this for years. And that's the speeds and the GLOs that we went to. This is what it looks like in the test cell. Pasted on here are pictures of the 2 different sets of, we had 2 antennas running. We can read multiple sensors with 1 antenna. In this case, we had 6 sensors with 2 antennas, each one reading 3. And so then we turn it on and it's very loud and fun, and you can see the sensor readings on the different antennas as it's rotating and operating full throttle. Just a closer look at what this is what our software looks like when it's working in real time while the turbine's running at, I think this is 80% throttle. This is the temperature data that we got. So for one of the first times that we're aware of, we've got, with no slip ring, because we're kind of the anti-slip ring company. With no slip ring, we were able to install these sensors, install the antenna without being intrusive, and get the temperature of the actual blade metal on the last row blade of the turbine, not the compressor, that's the cooler side, but the outlet side of the turbine, to tell you what the blades are doing on this test run. You can see us going from 10% throttle up to 80%, and then they had to do a quick shutdown because something was wrong with it, and then idle it 10% again, showing temperatures all the way up to near to about 850 or 870 degrees centigrade. Then we did other tests as well, and got data like this, going from 10 up to 50 up to 70% throttle. And so we have this system. It's a complete functioning system. It's commercialized. This is not the only test. We've done many, many tests with many different customers, but we wanted to tout this test that we did with Embry-Riddle. They're very good partners. And so we can use this to do real-time testing of new designs, things to do online condition-based monitoring, to see if anything's gone wrong, to see if the cooling, and then also to test to see, hey, I can reduce the cooling flows because I'm running cooler than I thought, and therefore increase the efficiency and fuel efficiency of these aero engines. And then as an aside, these sensors and antenna also work as is in a very high magnetic field. So you can use them in electric motors and generators as well, because neither the sensors nor the antenna form a closed conductive loop topologically. So they're not affected at all by magnetic fields. And so I just wanted to open it up for questions.
Is there any question?
I guess I have a question on the sort of setup. I mean, it looked like a monopole antenna. I guess you call it an interrogator.
Yes.
Can you go back to slide 11?
Like that?
Yeah. So what am I looking at? So I get. Can you?
Sure. So let's use the laser. All right. So this is the antenna, and it's sitting there. This is the back of the engine, and the blades are rotating around like that, right? And so we feed in our 10-foot long antenna, and then it is, when the sensor, which is a little bit offline, right, when the sensor's passing through in this area, that's when we pick it up. So we ping the sensor and read the sensor in a few dozen microseconds as it's passing by. This then is connected outside the engine over here. I've got my little Copper Mountain RF transceiver, which is then connected through a digital line to a laptop that's another 20 feet away or whatever. And that laptop runs the software that takes the frequencies detected by the Copper Mountain RF transceiver, and then converts them in real time to temperature. It displays them on the software and logs them.
Okay,
Does that answer your question?
Yeah, rigid antenna with your sensor embedded on that.
Right, this is the blade with the
Yeah,
sensor
blade.
on it, and then this is my antenna that's going into the hot gas path. So they're about, that far from each other at the closest path. This is rigid but bendable, so I can bend it with my hands, but I couldn't bend it with my thumb, if that makes sense. So it holds its place in the hot gas path really well, even though I can kind of.
So this is more of a stationary test to that point then?
Well, I mean, the antenna is stationary, right? But
I'm sorry, like you wouldn't use this in an environment like up in the air and then like that, you would use it?
no, it could be integrated into, like, the components are very light and small and durable, and so we also are working on an antenna that instead of being in the hot gas path, actually we have versions that would just be flush with the hot gas path and sort of angled like diagonally. So we have versions that we're working on right now that don't intrude into the antenna doesn't intrude in the hot gas path at all. So then that's more designed to be something that can be flown.
So you mentioned on the last slide that you have other versions or multiple sensors can be implemented to improve the accuracy? Or like on your conclusions, you said you could have multiple sensors for better accuracy, I think you said?
We can do multiple sensors in order to measure different parts of the blade, because it changes a lot from the root to the tip of the blade. So that's usually what you use them for, or as backups in case something happens.
So you mean you're having multiple on the same blade, you're not putting multiple on multiple blades
Oh
necessarily?
yeah, we'll have multiple. Well, like what I like to do is to have on that full wheel of all the different blades, have 4 sensors, one at 90 degrees, and like 2 of those will be near the tip, and 2 of those will be near the root or something. And we can measure that all with 1 or maybe 2 antennas.
And if you have a localized failure, I'm assuming that will affect more than itself, basically. Like, let's say you have a blade on the opposite end that has a failure. That will change the temperature distribution of the entire turbine, or just there?
Downstream it might, but usually what happens is that, like, the thing that they're worried about the failure mode is not that the blade is throwing heat, but that the blade is structurally failing mechanically. But that's usually a strong function of temperature. So what blades usually fail because they get too hot. And so we're trying to detect that before it becomes a problem.
And I guess my question is then, how representative is the temperature on blade on this side versus that side, then if you're sensing it on this side only?
Oh, right, so you're saying if there's a problem with blade number 3 and I'm only instrumented blades number 17 and 22 or something?
Something like that.
Right. No, we wouldn't be able to detect that.
So multiple sensors could be on multiple blades.
Right, so one of the studies that we're doing with a company, a commercialized company right now that works a lot of turbines, is that we could put the exact same identical sensors onto all the blades. And then what we would create is a reading, and we wouldn't necessarily know which sensor is which, but we would be able to create a Gaussian distribution of what those different sensor temperatures are and look for outliers on that. And then we would know that one of them is bad.
Maybe just not an RF question, but what kind of RPMs do you need to get to that? Was it 45,000 G or something like that? Any idea like what kind of RPM the turbine is spinning at to get those Gs?
And this one is 16,000, so the radius is on the order of about 11 inches or so. And so at 16,000 RPM, you get to about 45,000 G. This system doesn't need to be spinning to work, by the way. It's not inductively powered or anything. It works when it's still or spinning slow or spinning fast. The system doesn't really care.
Is there a dependence on the accuracy of the sensor with respect to the RPM?
There can be. So as we get to really, really high RPMs, something like 20 to 50,000 or something like that, the software is not, or the transceiver, we have to reduce the number of points to make the sweeps fast enough to catch the sensor well. And so by reducing the number of frequency points per sweep, then we lose resolution. Is it 5.01 or 5.03 gigahertz? And then that resolution translates directly to a temperature resolution. So sometimes at higher speeds, then we do that. You can use averaging because the digitization error is effectively a random thing. So we use averaging to handle that. But yeah, that reduces our resolution a little bit.
So how do you, does the frequency output change with the speed of the sensor? Because I would have thought there'd be some kind of Doppler shift happening, or does that not happen?
There might be a Doppler shift, but if you do the math on it, since we're at the gigahertz level and these things are going by at the speed of sound, it's way down in the noise. It'd be the equivalent of like I think I calculated that because I had the same question when I first joined the company. I was like, oh, all right, what about Doppler? And I calculated that it was 0.03 degrees centigrade is the Doppler effect in our worst case scenario. But these things are about as accurate as a type K thermocouple is about how accurate they are. So which is like 1 degree C, a little bit better, 0.8 to 0.9 degrees C. And we have versions that are 0.4 degrees C accurate, so we're not anywhere 0.0 something.
So I'm looking here at this bottom plot where you're showing the frequency domain, right? Because you're basically taking a Fourier transform of that ringing, right, to get essentially where is some frequency peak.
Yes.
Yeah, right. So do you ever have issues with SNR in there based on certain, RPM speeds? Have you looked into any ways to like suppress side lobes when that happens, or do you not ever have that issue?
We sometimes have that issue, right? And so we found that by changing the size of the sweep, like basically what happens is that you get it's a combination of different types of things to do with the Fourier transform and the size and the sweep length and the time domain and how much my delays are. That all factors into the math of the Fourier transform. So by playing around with that, we can usually get to a favorable SNR. But sometimes once in a while, we struggle and stuff will come up. But typically we get readings that look, pretty good. But sometimes we have reflections come up and we just make adjustments. We can real-time adjust the software on the electronic side in order to help deal with that. And there's other types of filtering that there's other types of filter we bring into bear in real time as well. We have a bunch of knobs we can turn in the software